Um, these these line segments are different than just like a basic line segment in geometry. The key there is that there is some direction. So it has an initial and a terminal point, and then there's like an arrow showing like which one is the start and which one is the end. Okay. So has magnitude, has direction. In terms of mathematics, when we talk about the magnitude of the vector, we're often maybe talking about, you could say its distance, or you could describe it to as its length. Okay, so that would be the same thing as a magnitude. And then a direction. There are a couple different ways that you can see direction. The first way we'll see direction is as a slope. And the second way that we'll see direction is as an angle. So magnitude and direction. Zach, you want to take your AirPod out? If you're not playing music, there's no reason to have it in your ears. Okay? I just ask for a little bit of respect that you not wear your headphones in class. Okay. What would be true if two vectors were equivalent? They have the same magnitude and they have the same direction. Excellent. So make sure you've got that down on the next part. Same magnitude, same direction. So the next slide is the one slide in the presentation that isn't actually included in your notes. I don't think that you necessarily need to write this example down. You can always look. There's a similar example in the textbook if you're having trouble on the homework. But it's going to ask about two vectors if you could show that they are equivalent. So show that they have the same magnitude and the same direction. Okay, so it might look something like this. So it says, show U and V in the figure at the right are equivalent. If you want to say that two vectors are in fact equivalent, you have to have the same magnitude and you have to have the same direction. An easy way to go about this is for these two vectors, U and V, you might just like by eyeballing it be like, yeah, they look like they're the same length and they look like they're going in the same direction, right? But you want to mathematically support that. So for same direction, an easy way to do this on the coordinate plane is slope, rise over run. So here's my starting point. I have to rise 1, and then I run 3. So the slope of U is equal to 1/3 positive, okay, in the direction of my arrow. And if I am looking at V, I start here at R, which is at 2, 2. I go up 1 and over 3 to get to 5. So the slope of V is also 1/3. So I've shown mathematically that they have the same slopes. Could I have used the slope formula y minus y over x minus x? Yes. But I really like to just kind of like use my rise over run method. Now I've created two right triangles. Okay. For magnitude, that's the same thing as distance or length. How could you find the length of U and the length of V? Pythagorean theorem. So the length of U is, let's say, the square root of 1 squared plus 3 squared. Okay, because I would add up my legs squared, so that's the square root of 10. And the length of V, obviously, is the same thing. So if you see a question on the homework about like show that these are equivalent, it's not enough to say, yes, they do appear to have the same length and direction. You want to show that, okay? So you can do some of the formulas. Pythagorean theorem, you could have also used the distance formula, okay? But I think Pythagorean theorem and rise over run are probably a little faster. Okay, let's talk about standard position vectors. A vector is defined as being in standard position if The initial point of the vector is at the origin, so at 0, 0. Now, not all vectors are actually in standard position. Okay, like we saw vector v on the last slide was like kind of like up and off to the right. But you can still take any vector out in the coordinate plane and you can write it in component form. Okay, if it's in component form, that would mean that it is in standard position. It does have a starting point at 0, 0. So component form looks like v equals, and then you have angled brackets instead of parentheses. So this is going to be important. If you're using parentheses, you'll lose points. You got to use the correct notation. Okay. And there's a v sub 1 and a v sub 2. So every vector has two components. The first component, v sub 1, is your horizontal component. And v sub 2 is your vertical component. Now, if you're coming from some physics background with vectors, you might be thinking about the word force. Okay, a vector as a force, and we're going to get there in 6-4. So that also represents like the horizontal component of force and the vertical component of force. So we'll get there eventually, but right now we'll just say horizontal and vertical. Think about how component form is very similar to an ordered pair, right? X, Y. X, the first thing is about left, right. Y, the second thing is about up, down. That's v sub 1 and v sub 2. Okay? But we use the angled brackets. Not every vector that you'll be working with will always come in component form. So off to the side, let's write how to get component form one time. Okay, if your vector is not already in standard position, having a starting point at 0, 0, then it will have some initial point, we'll call it x sub 1, y sub 1, and some terminal point x sub 2, y sub 2. So where does it start, where does it end? You gotta know those 2 points. If you want the component form, then subtract your horizontal components, x sub 1 minus x, or sorry, x sub 2 minus x sub 1, and subtract your vertical components, y sub 2 minus y sub 1. Now, to make sure that you have your vector going in the correct direction, you have to do your subtraction terminal minus initial. So notice I have my x sub 2 in the front there, minus x sub 1, and y sub 2 minus y sub 1. If you subtract in the other direction, your vector, or subtract x sub 1 y minus x sub 2, your vector will be going in the wrong direction. Okay, magnitude. Remember, if you need to rewrite like distance or length, make sure you know what is being asked of you when you're calculating the magnitude of a vector. The magnitude of the vector, we can simply say, as terms of a formula, is just the Pythagorean theorem. Okay, so v sub 1 squared plus v sub 2 squared. Remember, in component form, if you had a vector v, let's call that v, it has two components, v sub 1 and v sub 2. V sub 1 is its horizontal component, v sub 2 is its vertical component. So we're creating a right triangle. And if we're trying to find the length of V over here, we're just doing Pythagorean theorem. So that's all that we see up there. There is a new notation for magnitude. It's the double-sided bars. So that's not like an absolute value or anything like that. You read that as the magnitude of V. Okay, see if you can do the example on the right. Okay, find the component form and the magnitude given the initial and terminal points. Terminal minus initial up there. Okay, when you're asked to write something in component form, remember you're looking for two specific components, horizontal and vertical. In order to get them, I'm going to do terminal minus initial. I'm seeing a few small errors. -7 minus -2 is actually +2, so that's going to be a -5. Make sure you adjust. And 6. So there's your component form. To calculate your magnitude, we can say the magnitude of V is the square root of our horizontal component squared and our vertical component squared. So that's 25 plus 36. What is that, 61? Okay, the magnitude of V is 61. Square root 61, I should say.
Would you want us to leave it as a radical?
Yeah, I would say most of the time in vectors, we're just going to leave it in exact form. So leave it as a radical. Of course, if it could be simplified, you would. Like if it were the square root of 60, then 60 has a perfect square factor of 4 times 15. So 2 square root 15 would be the appropriate answer. But yeah, I would just leave it as a radical. Okay, so we know its distance is between, what would that be, 7 and 8? Closer to 8. Anybody got any questions so far? Okay, let's talk about a unit vector. Anytime in math, when we talk about unit things, something very special is that it has some measurement of 1 unit. So we talked about the unit circle a lot in chapter 4. It was special compared to all other circles because its radius was 1. So a unit vector is a vector whose magnitude or length is 1. Now, certainly not all vectors have a length of 1. Do you agree with that? Like the one we just found was almost 8. Okay, square root 61. Okay, if you want to get a unit vector in the same direction as a vector that isn't a length of 1, you just divide the vector by its magnitude. So what that means is if you have like a longer vector, you divide it by its magnitude, it's going to scale it back, okay, to be a length of 1. Or if it's a shorter vector, it's going to scale it up to be a length of 1. Let's find the unit vector in the direction of 7, -3. So first things first, let's find the magnitude of this vector. Magnitude of V is the square root of, I could say 49 plus 9. Are you okay with that? So square root 58. Is V a unit vector? No, because its magnitude is square root 58, also somewhere between 7 and 8. Okay, not a unit vector. does not have a magnitude of 1. But we want to find a unit vector that goes in the same direction. So I'm going to call that u. To get u, just take your vector 7, -3 and divide by the magnitude. If you divide both, or you divide a vector by some number, you're really dividing both components by that number. And then what would we want to do in terms of final answers if we want an exact answer? Get that square root out of the denominator. We call that rationalizing the denominator. So just like make everything clean at the end, right? Okay, so that will bring up a square root of 58 into your numerator. So this is 7 square root 58 over 58 and -3 square root 58 over 58. So that's going to be my unit vector. Okay, so what should be true about that vector? Its magnitude is 1. Should have magnitude u equal to 1. If you want, you could go through the work and do u sub 1 squared plus u sub 2 squared and then square root it. I will tell you, it is in fact 1. Okay, so we have scaled it down to the correct length. You got any questions for me on the unit vector? Maybe like square, highlight, circle, something, that second bullet point, divide the vector by its magnitude. You're trying to scale it up or down to 1. Okay, on the back side, we're going to talk about some vector operations. Okay. What I think you're going to find is that vector operations are very easy math. Okay. The hard part about vector operations is like, what do these things actually mean? So we'll fill in the blanks on the left. We'll do the examples on the right, and then I'll try to show you visually like what all that stuff is actually talking about. Okay, so actually we just did scalar multiplication. To create the unit vector, we just divided by square root 58, which is like multiplying by 1 over square root 58. Just like with matrices, when we had scalars, you have to distribute it to all the entries. So if you have a scalar in front of a vector, you just distribute it to all the components, horizontal and vertical. The one thing to note is that if your scalar is negative, your vector will change direction. I'll show you that when we do the subtraction problem. Vector addition. Geometrically, what you're doing is taking the initial point of your second vector, so the starting point of the second vector, the thing you're adding on, and you put it at the terminal point of the first vector. So you can sort of think about adding vectors as connecting the dots. Okay, you start the first one at 0, 0, like it was in standard position. Okay. And then wherever it ends, you just build off from there. And however many vectors you add, you just continue on from that terminal point. In subtraction, you want to not like go in the same direction as the second vector, because that would be adding it. You'll go in the opposite, because subtraction is plus a negative, so it's like having a negative scalar. Your second vector will go in the opposite direction. Okay, and I'm going to show you the visuals for this when we do our example with adding and subtracting. The last thing to note, and this is a really good vocab word for people because sometimes people get confused in their homework. They're like, it asked me about a resultant and I don't know what that is. It's the answer to your addition or subtraction. Okay, so like I said, addition and subtraction and even scalar multiplication, they're all very easy math jobs. So let's let u be the vector 1, 4 in component form, and vector v be 3, 2. We're going to add the two vectors. First, I'm just going to do it math-wise. If you're adding two vectors, u and v, add the horizontal components together, add the vertical components together. So this is going to be 1 plus 3 and 4 plus 2. Don't know what I'm doing. How about 4, 6? It is supposed to be easy math. You can make mistakes, just like me. Oh, and this is like nothing now. It looks weird. There we go. Okay, so we just add the horizontal, add the vertical. This right here is your resultant, right? Here's what just happened. I started with a u, which would start at 0, 0, and has horizontal component 1, vertical component 4. So looks something like this. There's u. Okay. From the terminal point of view, I'm going to connect the dots here. I'm going to be adding v onto that. So that means I'm going to go right 3 and up 2 from this point. I'm going to add in my right 3s and my up 2s. So I'm going right 3 and up 2. And there's my v. And then think about your resultant vector, horizontal component of 4, vertical component of 6. If I went right 4 and up 6, I would land at this terminal point, right? So the resultant vector, if you want to think geometrically, is kind of like after you connected all the vectors, it's closing that shape. Okay, it's that new vector from the origin to your last terminal point. Okay, can you try B and C if you haven't already? See if you can do u minus v and 2u minus 3v for me. Careful with your signs and just simple addition and subtraction. If you want to show work, you're doing 1 minus 3 and 4 minus 2, so you should get a negative 2, 2 for subtraction. I want to show that one to you visually because we wrote about it over on the other side, that your second vector should go in the opposite direction. So u is still 1, 4. I'm still at that point. But if you're subtracting v, instead of going right 3 and up 2, you're going to go in the opposite directions. You're going to go left 3 and down 2. So I would start at this terminal side. I'm going to go left 3. I'm going to go down 2. That's like negative v, the opposite of v. And so your resultant vector of negative 2, 2, it's still this little piece here from the origin 0, 0 to your final terminal point. Okay, negative 2, 2. Okay, that's u minus c. Feeling okay? Okay, 2u would be what? 2, 8, and 3v is 9, 6. So if I subtract those, I'm doing 2 minus 9 and 8 minus 6. So I get a negative 7, 2. Visually, what would happen, I won't take the time to graph that one, but visually what would happen is I would actually be graphing those longer vectors that were multiplied by 2 or multiplied by 3. So I would go like right 2 and up 8, because that's 2 times the original u. And then I would add on the larger vector v. I would go right 9 and up 6 from there. Oh, sorry, subtract. I would go left 9 and down 6. Okay, next up we're going to talk about standard unit vectors. So again, there's that special word, unit, right? What does unit mean? Has a magnitude of 1. Now, these are not just any old unit vectors. They are the standard unit vectors. And standard means we have one for horizontal and one for vertical. So this vector, you go 1 unit to the right, you go 0 up or down from 0, 0. Wouldn't you agree our distance would be 1? And this one is 0 left or right, 1 up. So again, our distance would just be 1. So they are unit vectors. Specifically, they are going right and left. Okay, now this part used to rewrite the vector as a linear combination of vectors I and j. This is one of those things where, again, like, get the practice that you need with, like, the vocab of vectors. We don't really talk a lot about linear combinations leading up to this point. Mathematicians, we talk about linear combinations as things in the form of like an ax plus by. So a and b are generally like some constants, and then x and y are 2 variables, and we call that a linear combination. So there are 2 things that are getting added together, 2 products. Make sure that you get this part down. You can take any vector in its component form, v sub 1, v sub 2, and without any work at all, you can change it into a linear combination. It'll look like v sub 1 I plus v sub 2 j. Okay. So what that means is, like, on your homework, on quizzes, on tests, I can present a vector to you in either form, and you know what the horizontal and the vertical components of the vector are. If I gave you 2, 3 in component form, we could rewrite that as 2i plus 3j. They are the same thing. I don't have to do any work. If I gave you negative I plus 5j in linear combination, then without any work, that is negative 1, 5 as a component form. So this is just a new form you can change in and out without any work. So see if you can get the linear combination for the vector in the example to the right. Pay attention to direction there. You want the linear combination. See if you can get the correct form for me. Since you're given an initial and a terminal point, what might you like to find first? The vector's component form, right? It's horizontal and vertical components. So you might have to find the horizontal and vertical components of the vector first. You don't want to use the ordered pairs. Those are vectors. Find the component form. Just check your calculation. Look back at that example. You don't have the word written down. So I'm not sure how you got those numbers. How do you get component form when you get an initial and a terminal point? Subtract terminal minus initial, right? For horizontal and vertical. So this is U. Terminal is -3 minus 5 and -1 minus 2. Terminal minus initial for the vertical component or horizontal component. Terminal minus initial for the vertical component. That's -8, -3 in component form. But the direction says write it as a linear combination, so we will lose points if we leave it in component form. So I change it to a linear combination. It's -8i plus -3, but I'm going to write mine as -3j. That's linear combination form. Be careful. These things are not correct linear combination forms. Wrong. It has the brackets. It shouldn't have brackets. It has a comma. It should have a plus. Wrong. Shouldn't have brackets. Wrong. A linear combination is a sum of two products, ax plus by. Should have a plus. Don't write those. It's got to be -8i. You can say plus -3j or -3j. Questions, concerns? All right, last thing is going to be direction angle. A direction is the measure of an angle between the vector and the positive x-axis. Okay. I'm going to start with the vector here in quadrant 1. We're going to see this a lot coming up here in chapter 6. Do you agree that for this particular vector, it has some horizontal component, v sub 1, some vertical component, v sub 2? Okay. What did I just create right there? A beautiful right triangle. Okay. And we want to find the angle between the vector and the positive x-axis. So here's my vector. My positive x-axis is here. That would be theta. What would you use to calculate theta? you know its component form, v sub 1 and v sub 2. Trigonometry, specifically, which trig function? Tangent. You have the opposite and the adjacent side. Okay. So we can say that theta equals the inverse tangent of v sub 2 over v sub 1. Or if you prefer to write it and then solve, you can say tangent theta equals v sub 2 over v sub 1. I like to just use the inverse tangent form. Okay, so you could calculate your direction angle there. Okay, but there are 2 bullet points here that are really important. Be aware, a direction angle should be a positive angle. It should be between 0 and 360, so 1 full revolution of a circle. I'll let you use degrees because that probably makes the most sense to us. But be aware of which quadrant your vector lies. So I'm going to draw 3 additional pictures up here. They're going to be smaller, but I'm going to put a vector in each quadrant. So there's V, there's a V, and there's a V, right? Quadrant 2, quadrant 3, quadrant 4. If you follow the definition of a direction angle, it's from the vector all the way to the positive x-axis. So think about this angle. It has to be, if you're in quadrant 2, it has to be between 90 and 180. If you're in quadrant 3, then theta has to be between 180 and 270. And if you're in quadrant 4, your theta has to be between 270 and 360. You okay with that? Okay. You will have some issue in your calculator because going back to chapter 4, arctangent, if you're in degrees, is going to give you something from negative 90 to positive 90. So you'll have to make the adjustment, whether you're adding a 180 or a 360, so that your angle makes sense for the quadrant that it's in. I'll show you in my 2 examples. Let's find a direction angle for 3, 4. Can you just mentally picture what quadrant is 3, 4 in? First quadrant. So think about what your answer should look like. If you're in quadrant 1, your angle should be between 0 and 90. This is my v sub 1, this is my v sub 2. I know that theta is the inverse tangent of 4 over 3. Okay. If you know that, we're going to use it so much in the next sections, then you don't have to draw a picture. But if you're unsure, you can always draw yourself a picture. So say that you're going 3 and 4. And then you would know to do an inverse tangent, right? Okay. What do you guys get in degrees? 53.13, thank you. Does this angle, 53.13, make sense for quadrant 1? Yep. So I could just be like, yep, that's my answer. Let's think about B. What quadrant will negative 3i minus 10j be in? Quadrant 3, because we're going to go left 3 and down 10. Okay, so this is going to be in Q3. I can still do theta equals the inverse tangent of the vertical component over the horizontal component, which will be negative 10 over negative 3. What does your calculator say? 73.3. Does that angle make sense for quadrant 3? No. Add 180 degrees. It's like the 73.3 is kind of like that reference angle. It's the overflow into quadrant 3. So then we can add 180 to it. We'll get, what, 253.3 degrees? Does that angle make sense with quadrant 3? Yeah. Okay, so this one works. This one doesn't. So our answer should be 253.3. If you land in quadrants 2 or 4, the calculator is going to give you an angle that is negative, because you'll have a negative ratio for tangent. So you can still, like if you're in quadrant 2, take that negative angle, add 180. It'll be less than 180, but more than 90. Or if you're in quadrant 4, add 360 to it. It'll be less than 360, but more than 270. So always be thinking about what quadrant you're in. All right? Okay, you have a homework assignment. It's on the gold sheet. It's really not a bad assignment. It looks like a lot of problems, but really, like, your vector work is very quick, right? Direction angles is something that students often struggle with, making sure it's in the correct quadrant. And then that whole linear combination, changing form, it should be so easy. Don't overthink it. It's just another way to write a vector, but it's the sum of two products with I and J. Can you also remember that you have quiz correction?